So today we'll be looking at how to make our own custom motion lights. So let's start from the beginning. Okay, so moving on, let's have a look at our schematics. So you can see a master side and a slave side with wireless connection between them. I'll tell you the reason behind this nomenclature later on. First, let us have a look at the master side schematic. So first, let's have a look at our core MCU ATmega16A. We have a reset button for the MCU, a 8 MHz crystal oscillator with load capacitances, and a bypass capacitor for the power supply. Next, we have the ISP connector, responsible for programming the chip over SPI protocol. I've already covered a video on how to program our Atmega chip using a USB ASP programmer over SPI. Next in line comes the motion sensor. So for this project, we have tested three of the common found sensors. One based on Doppler effect, other based on passive infrared sensing, and the third one, the ultrasonic sensor. Out of these three, for this project's sake, we moved on with a passive infrared one, but it is recommended to often incorporate two sensors together and fuse their data to get the best result. An LDR is used to check the lighting condition of the room. For RF communication, we'll be using nRF24L01 based chip, which also works on the SPI protocol. Also, you can connect a 10 microfarad capacitor between the power rails of the chip for improved power supply. Next in line, we have a relay which is triggered when motion is detected. The power supply for the LED strip comes from a LED driver which provides 12 volt to the LED strip. Voltage regulator is used for 5 volt and 3v3 power supply generation on the board. So the main motto of this project was to have two nodes separate from each other and communicating over the RF mode. Earlier my thought was to make one a slave while other the master, wherein the slave only has one duty and has to send messages over RF whenever a motion is triggered near it, while the master does not send any messages to the slave and just receives messages from it and turns on the light in advance. While you are completely free to use it as this example. But later on, what I did was I made both of them a master in their own sense, wherein they can operate independently whenever motion is triggered near them, as well as send a RF message to the other one so that the lights are turned on in advance. Obviously, a certain timeout would be needed, in which if you don't reach the other node, it will turn off the lights. Rest all the components of the nodes are similar to what I have already shown you in the master side. So enough with the schematics section, let's move forward. So finally, it was time for some shopping and unboxing the components. So now it was time to assemble all the components together and start soldering. So finally, both of our boards are ready and we can proceed with uploading the code. But before that, I would like to make a comment. So I've used this board which provides 12 volt, 5 volt and 3 power supplies. So this board has a 5 volt and 3 voltage regulator on it. While I've used this, you can use both the regulators separately. This board has a jack and I've connected it with a 12 volt DC adapter. You can also power your own board with a lithium ion battery or a 9 volt battery. The battery circuits are pretty simple and can be easily found online. For now, we would be skipping the procedure of uploading code as it has already been covered in an earlier video. Okay, so let's now talk about our core MCU, that is ATmega16A. As you can very well see, it's an 8-bit microcontroller which is based on RISC architecture. You might be familiar with RISC and CISC architecture. If not, you can search it online. Still, I would like to point out few things about RISC architecture. So, in a RISC architecture, the number of instructions as in what you want the CPU to actually do. So, the number of instructions in a RISC architecture are lesser as compared to CISC architecture. Now, because of this, sometimes for the same logic to be developed, more number of lines of code are required in a RISC architecture based CPU. Due to this, code space required is much more. But that won't be a problem because nowadays flash memories are becoming cheaper and cheaper. Now you could program your Atmega based chip using any ISP programmer. There are plenty available, but in the end, they would be using either SPI or JTAG based interfaces. So JTAG based interfacing devices also provides you with the debugging feature, which is not available in the SPI based programmers. We have programmed it using an USB ASP programmer, which doesn't support debugging. So this device right here comes in different packages, and we have selected the PDIP package. As you can clearly see in the pinout, TDI, TDO, PMS, TCK. These are the pins for JTAG page programming, while MISO, MOSI, SCK, and Reset. These are used in the USB based programmer or SPI based programmer. So this is the block diagram of our controller. As you can see, it has different buses and peripherals, as well as our main CPU. The main CPU has a program counter, a stack pointer, a ALU, some internal registers, which are 32 in number, each 8-bit wide, a status register. So basically, program counter points at the next instruction in your code memory. Stack pointer is responsible for pointing to your internal SRAM. Status register exactly keeps account of what the result is. If the result has a carry, if the result is zero, if it's negative, if there's an overflow, things like that. The flash memory on this device is 16 kilobytes and it is organized as 8K cross 16 bits or 2 bytes. So it eventually gives you 16 kilobytes. Also, this flash memory is divided further into two segments. One is for your main application code and other is for your bootloader. So bootloader helps you to push the program through other interfaces like USB or UART, for instance, something what Arduino uses. Next is our data memory map. So, as you can see, 1024 bytes or 1 kilobytes are separately kept for our internal SRAM, while we have certain memory addresses for GPR or general purpose registers within the CPU and SFRs, which are special function registers of the peripherals in this controller. There is the summary table of all the available registers in this controller at the bottom of the datasheet with its relative and absolute addresses. Also, instruction set summary is available just below register summary. So, this here has all the instructions that are accepted by the CPU. along with the clock cycle needed for its implementation. Remember, clock cycle depends on the clock frequency of your controller. In our case, we are using an 8 MHz based external crystal oscillator. Under the system clock table, you can clearly have a look at various clock options that can be used, be it an external RC oscillator, an external clock signal, crystal oscillator, internal calibrated RC oscillators. So, in order to select your clock option or clock source, you have to set CKSEL bit in the fuse bytes. Default clock source for your chip is 1 MHz internal RC calibrated oscillator. Let us now talk about our RF transceiver NRF24L01. This also uses a 2.4 GHz ISM band, which is shared amongst Bluetooth and Wi Fi. Hence, we should take care in assigning the channel for our RF communication. Well, the most important feature of this chip is enhanced clock burst. This takes a lot of load away from our main controller. Some of its features are calculating CRC for the transmit packet and checking the CRC bits of our received packet. It also takes care of packet loss, and it also keeps account of how many auto read transmit has already occurred. Automatic acknowledgement is also a critical feature wherein a PRX or primary receiver switches its state and sends an acknowledgement back to the PTX or primary transmitter, and it checks and approves if the message is sent properly or not. A table with all the register maps is also available in the datasheet, along with all the commands that needs to be sent over SPI. As it is clearly stated here, in order to achieve auto acknowledgement in a PTX device, data pipe 0 should have the same address as the transmitting address. So here is an example wherein a receiver is connected to 6 other transmitters because each device has a limit of 6 data pipes. From pipe 1 to pipe 5, the addresses only change in their last byte. As you can clearly see, RX address P4 of our RX device is B3, B4, B5, B6, 0F, while the TX address of TX4 is the same, as well as the RX address of P0 of our TX4 transmitter is also same because of earlier discussed auto acknowledgement being enabled. So all the candidates of the motion sensor, which is PIR, ultrasonic, and Doppler radar sensor, they were tested using an ESP32. The conclusion was made that Doppler effect sensor was too sensitive and alone cannot be used in an indoor environment, while the field of view of an ultrasonic sensor was much less. That's why I eventually went with an PIR sensor. But as I said earlier, it would be better to incorporate two sensors. In our case, a Doppler effect sensor with a PIR sensor is usually what is used in motion sensors, which is available in the markets. It for now. Hope you guys liked this video. If you did, do not forget to subscribe, as that would motivate me further to make such kind of videos in the future. फिर मिलेंगे